Commissie entrance exam physics of last time, November 2023. In a month or so there will be a next exam. So this will be good practice. Question 1 is about silver ore. Silver is found in subterranean rocks. It's extracted from the ground to the surface by a train. A train is powered by an electric motor and starts its journey upwards. And figure 1 shows the VT, so velocity time diagram, of the first 130 seconds. And yeah, so this is a one-dimensional motion, if all is well. We hope so for the train. And the velocity is on the y-axis, the time is on the horizontal x-axis. And then they ask to determine the distance the train traveled at t is 80 seconds. Okay, so from a VT diagram, you have to remember that it's, first of all, how to find the acceleration, instantaneous acceleration by looking at the slope, and secondly, what is the meaning of the area under a VT diagram. And given that velocity is defined as a change in position, a displacement, divided by a time period. And if you just rearrange it a little bit, you get that displacement is the velocity times the time. And from this, you can easily remember that the area under, since these are kind of area elements under the VT diagram, is equivalent to a distance traveled, a displacement. So, well, let's do that. Let's get this thing on the paper here. And yeah, so we have to go from 0 to 80 seconds. So we need to figure out what this area underneath is. So it's just a matter of counting blocks. And one block in this is, well, horizontally it's 20 seconds. So if 20 seconds times, vertically one block is 0.5 meter per second. So that comes out at 10 meter. So every block underneath means a displacement of 10 meter. Now, of course, the curve is cutting a block in two, so you have to estimate. There are actually several ways to do this. You can, but what I would do, and I think that would be counted correct, is just to estimate for these blocks what is the roughly the fraction of a block that's included. So here, this area would be roughly 0.3 block, and this perhaps 0.9. Maybe even you can approximate it to 1. And here it's about a half, or say 0.4. Now these are clearly 1. This one is probably 0.9. This one is, say, 0.5. 1. Again, just do your best estimate and write down what your assumption was, and that will be good enough. I would just say this is 1. This is 0.6. So now we're to 80, and now it's just a matter of counting blocks. So here we have 0.3, 1.3, 3.9, 3.4, 1, 2, 3, 4, 5, 5.6. Oh, wait, here. Okay. this one, this block is also actually being cut, but I can just set this at 0, and maybe this is, oh, let's say 0.1, this 0.2, and here another 0.2. So I have 0.3, this is 1.4, 2.9, 3.4, 3.6, 1, 2, 3, 4, 5, 5.8. So now I need to add these, and out of laziness I will use the calculator for that. It's 11.1, so the sum of these is 11.1 blocks. And then I need to multiply that by the area of each block, so that is then 110, 111 meter. So that's our kind of rough estimation of it. Okay. There's some other ways you can subdivide. You can actually, oh, let me actually try that if I have time. Let's say I just digitize it, but in a very rough, inaccurate way. I would just say if more than half of the block is underneath, it's a 1, otherwise it's a 0. So this is a 0, this is a 1. This is a 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0. Then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 blocks. So even with that method, you get really, really close to it. Anyway, we need to think about time, so we just continue. I think we answered the question. All right. So they give the mass of the train, and then the figure we were just looking at shows that at t is 60 seconds, the train is still accelerating. Can we see that? Yes. The velocity is still increasing. Determine the magnitude of the resultant force on the train at t 60 seconds. Use figure 1 on the answer sheet. Well, I don't have the answer sheet, so I will just copy this again and see how far I can come. All right, so now how do we figure out the force? Well, we know that the force comes from the acceleration. If we know the acceleration of the train, we also know what the resultant, say the total force that's acting on the train is. So let's just do that. Let's find out what the acceleration is, and for that we need to figure out the slope of this curve at t seconds. So take your ruler and just put it at the curve at t60, and then in a way that it only intersects the curve once. So that's called a tangent, raakline in Dutch. Now there's definitely a margin of error there that is unavoidable, and actually not so easy to estimate, but okay, I think it's roughly this. So I draw my tangent, and one thing you definitely have to do, and if you don't, I think points will be subtracted. You have to go to all the ends of the graph. So you just go as far as you intersection of either the top or the right or the left, but in this case the bottom and the top. So that is my ruler, and now whatever this delta y is, well, that is 4, certain for 4.0, and that's given because it's the top line axis, so we can say these are all significant figures, so 2 significant figures here is appropriate. So then here we end up in 20, could be 19, but if we write at 20, basically you already say that this is the least significant figure. That actually could be 1 or 2, 1 less or 1 more, but we are, yeah, so writing that it's 2 significant figures is okay. And then here we are at, say, 90. And again, on your graph paper, I think you can do it a little bit better than I did here with my crooked factor here. But you get the message and 2 significant figures. So delta x is then 70 meter. And so the slope, you can see it from the, not meter, 70 seconds, of course. And I was going to figure that out because the slope has to be acceleration, which is meter per second squared. Okay, so the estimated acceleration at t is 60 seconds is then 40 divided by 70. Yeah, you can have the units here or not. I think both is fine as long as you keep the units in the final answer here. So where's my calculator? 40. It's 0.57 meter per second squared. Okay, and again, this 7 is not sure, but writing it in this way is fine. So now the force is simply the mass times this acceleration. So it's 30 times 10 to the power 3 times so that is 17. Let's put it in the scientific notation with the appropriate number of digits. I keep 2, so it will be 1.7 times 10 to the power 3 Newton. 15 degrees up to the entrance. It's shown in figure 2 with the center of gravity Z. Indicated on it, Z is from zwaartekracht in Dutch, gravity. It's shown with an arrow. Figure 1 shows that the velocity of the train becomes constant after some time. Yeah, that's true. After about 100 seconds, it becomes constant. The friction force is 25 kilonewtons. In figure 2, draw the other forces that act on the train at this constant velocity in the correct relationship to the gravitational force. Let all forces act at the center of gravity z. Explain the magnitude of the forces with a calculation. Alright, so what are the other forces? So they state there is a gravitational force Fz, and there is a friction force F, just F for friction. Well, what other forces are acting on it? There's, of course, the normal force from the ground, that ensures that the train doesn't drop down. So that will be perpendicular to the slope. Right. So that is a vector with a certain direction, but with magnitude Fn. And, well, if it's like this, there actually will be a resultant force to the left, so that's of course compensated by the motor force of the train that will go in this direction, Fm. So these are all the forces acting on it. But now the question is, what's the magnitude of this, of actually each of the forces? Well, they already tell us what the friction force is. The magnitude is 25, so 2.5 times 10 to the power 4 Newton. And Fz is, well, that's the gravitational for the force, the weight. So it's 30 times 10 to the power 3 kg times the acceleration due to gravity. So let's calculate that. Times 9.81 is 2.94 times 10 to the power 5 Newton. Alright, so 2 we already have. Now you need to draw them. Okay, what do we need to do? We need to draw them in the correct relationship to the gravitational force. Okay, so I don't know what the length of this in the graphing paper. Okay. But what we know is that, say if Fz is 1 centimeter, then F friction will be 2.5 times 10 to the power 4 divided by this. So let's calculate that. That is 0.085 centimeter. It is obviously much smaller than Fz. right? It's less than 10% if you look at the magnitudes here. Okay, but that's just part of the question. We also need to figure out what this Fm is and Fn. Well, the train is not accelerating, so all the forces must cancel. So it's most convenient here just to define the axis as x-axis as in the direction of the slope, and the y-axis perpendicular to that, and then just decompose Fc along this x-axis and the y-axis. So let's do that. So here we have our gravitational force, and here we have our slope. What we need to do is decompose it along this slope and perpendicular to it. And what we need to do is project this vector on this axis. So that is this by a 90 degrees angle. So don't do something like this here, right? It has to be perpendicular to this, and the same for the x component. So this is Fz, and let's call this component here Fcx, and this component, sorry, that's bad. Okay, Microsoft. Here, Fzy. So we have Fcx. Well, let's look at this angle. So we have this angle here is 15 degrees. And then you can already see where this angle should be here. Well, it's either here or here is to be 15 degrees. And the reason is that the sides of this angle are perpendicular to the sides of this angle. So this is perpendicular here, and this is perpendicular to this side of this triangle. There are other ways to figure it out as well. So what we have is, if this is the angle, then the sine of this angle is Fcx divided by the hypotenuse, which is Fz. So Fcx is just the sine of 15 degrees times Fz. So let's calculate that. Fc is 2.94 times 10 to the power 5. And I need to multiply that by the sine of 15. So that is 7.61 times 10 to the power 4 Newton. Makes sense. It's much smaller than the length of the 15 degrees. And I probably exaggerated the angle here a little bit, making this actually longer than it should. So when you do the drawing, actually make sure that your angle is right using your ruler. Then the y direction will be then the cosine of 15 degrees, right? The cosine of this angle is the adjacent side Fcy divided by the hypotenuse Fz. So I get again 2.94, and this is actually a lot of work. I'm taking a lot of time already, so that makes this all a little bit tough. That is 2.84 times 10 to the power 5 Newton. You see, it's much closer in magnitude to the value of Fz. Okay, so now we have this. Then we know that the motor force has to be equal to, the magnitude of this has to be equal to the magnitude of the friction plus this Fcx in order for all the forces to cancel. So, yeah, you can say even the resultant force has to be 0. So in both x and y, so we Fm, so the magnitude of the motor force has to be equal to the sum of these two forces. The friction force, 2.5 times 10 to the power 4 Newton, 7.61 plus 2.5 times 10 to the power 4, that is a total of 1.0 times 10 to the power 5 Newton. Now, if Fz is 1 centimeter, how long then do you need to draw it? So let me write equals with some sign that this is not really, that I converted it to a length. So I need to divide this by 2.94. So that would be 0.34 centimeter. And what else? So then the last one is the magnitude of the normal force. That is just equal to the y component, so is equal to 2.84 times 10 to the power 5 Newton. And let's convert this into centimeters. Oops. .94. That is 0.97 centimeters if Fz is 1 centimeter. So yeah, this answer is probably not correct because the actual length of Fc might be something else, but I think you can kind of catch the meaning. And let me see, what does this give? What? Okay, so here they say the length of Fc is 5.9 centimeters. So basically multiply this all by 5.9, and then you get the actual length at which you have to draw it in this question. But I will leave that open to you guys. Okay, that is actually all very time consuming. And we have to keep track of time. Okay, yeah, so in the end what you do is draw these 4 forces and draw them with the correct lengths. And then you should have answered this question correctly. All right. Hopefully these are not that much work. So when the train arrived at the top, it stops and ore is removed, then it returns along the same track and it stops at the same place where it initially left for the top. The track from bottom to top, and of course also from top to bottom, is 657 meters long. The mass of the empty train is this. Then during the journey down, part of the gravitational energy is converted into electrical energy by a dynamo, which is basically a generator. And there's a constant friction force, and as a result, part of the original gravitational energy is converted into frictional heat. And yeah, okay. And then of the remainder, 63% is converted into electrical energy. Calculate how deep the train is finally below Earth's surface. Okay, well let's draw it again. We have, let's see what we know. We know the slope. And we also know the length along the track, which is 657. So then we just can calculate this height here. So we have to take the sine, the opposite, divided by the hypotenuse. So we get the sine of 15 degrees equals h divided by 657. So h is sine 15 degrees times 657 equals to 170 meter. We keep three significant figures. Calculate the electrical energy produced during the descent. Well, they say that this electrical energy is coming from this 63% remainder of the remainder. So let's see. So the potential energy difference, so let's say delta E gravitational is the mass of the train times g times the height. So that is 6.0 times 10 to the power 3 times 9.81 times 170 meter. Let's calculate that. That is 1.00 times 10 to the power 7 joule. Now, not all this energy goes into electrical energy for two reasons. One reason is something is lost due to friction. So what is lost due to friction? Well, that's it's the work done by the friction force, which is equal to the force of friction times displacement. This is one of the key equations you need to know. This is where a lot of the energy-related items come from. So when a force is doing work, the work is given by this equation, the force times the displacement. And from this, for example, you can find out what the kinetic energy is of an object under a certain force. Now we know the friction force is 5 times 10 to the power 3, then times 657. Is 3 times 2.9 times 10 to the power 6 joule. So what is then the remaining energy? We need to subtract these. So they call it ER, remain. So 1.00 times 10 to the power 7 minus 3.29 times 10 to the power 6. Okay, I can which is 6.71 times 10 to the power 6 joule. But they say that 63% of this is converted into electrical energy, so electrical energy equals times 0.63 is 4, and let's round it, 4.2 times 10 to the power 6 joule. It's too soft to make jewelry, and so they add copper. An alloy of 92.5% of the mass consists of silver, and 7.5% of the mass consists of copper. Is called sterling silver. Such a piece of jewelry often says 925. A silversmith buys a block of silver on eBay. Oh, that's not a good idea. It weighs this, and this is the length and the width of the block. Calculate the thickness of this block as accurately as possible. Give the answer with the correct number of significant figures. Okay. Well, we know the mass pretty precise, and if you know the mass, and we know how much of the mass is silver and how much of this mass is copper, and if you know mass, you know volume by using the density. We know that the density of a material is the mass divided by volume, so the volume is given by the mass divided by the density. So we just figure out the mass of the silver, the mass of the copper, and find their densities in binas, and then we can calculate the total volume of the block, and we know the length and the width, so we can find the height. Alright, so what's the volume of the silver? That's then the mass. The mass is 9.25 times 2.500 and divided by the density of silver. Why is this not working? Okay. I just have the Dutch version, but it's easy to find in your English version. That's gegevens van vaste stoffen. Where is it now? need to rotate this. So here we talk about densities. Okay, here. Silver. 10.50 times 10 to the power 3 kilogram per meter cubed. And let's also write it down for copper. And we have 0.75 times 2.500 divided by 8.96 times 10 to the power 3. So 0.925 times 2.500 divided by 10.5 times 10 to the power 3. No. I put the decimal place wrong. Okay, see, this is so time consuming. That is actually the main concern I have with these exams. It's 2.2. Let's keep 5 significant digits as we go. 4 times 10 to the power minus 4 meters cubed. Then for the copper, we have this 2.0926 times 10 to the power minus 5 meter cubed. Okay, so the total volume, V total, is then just plug it in. Is that correct? It's 2.4117 times 10 to the power minus 4 meter cubed. Okay, so now we have the volume. We also know the width and the length of the bar. So that means the height is just then that volume divided by the width times the length, which is 0.110 squared in meters. I put it in meters, of course. So I divide this by 0.110 squared. So then I get 1.99. How many should I keep? Actually, 3 significant figures. Was 8.96. Yeah, 3 significant figures times 10 to the power minus 2 meter. So it's about 2 centimeters. Okay, now we go to 1F. If the silversmith accurately measures the thickness appears to correspond exactly with the thickness calculated under Part E. The block therefore has exactly the dimensions that a block of sterling silver weighing 2.5 kg can have. Explain whether the silversmith now is certain that he has indeed received a block of sterling silver. No, he just knows the density of the material, but there can be many alloys with the same density. As sterling silver. So he cannot be sure. Or there can be many alloys with the same density as sterling silver. Okay, moving on to question 2. A voltage source supplies a voltage Vs is 20 volt. This source is connected to the leads of a variable resistor RAC of 40 ohm. B is a sliding contact that can be moved between A and C. The positive side of the voltage source is connected to the earth via an earthing wire. Okay, so you can set this at 0 volt. And there's a switch here with a light bulb. And it's open initially. A voltmeter measures the voltage between B and C, and an ampere meter measures the current through the AC section. Copy the circuit in the figure and also draw the location of the voltmeter and ampere meter. Okay, let's copy this circuit. Draw the location of the voltmeter. Well, it's measuring the voltage between B and C. So it must be located here, connecting here to earth and here to the contact at B. Or you probably might also draw it like this here. And then also for the current through AC, so that current goes through, well, this direction, that it goes through here, and there's actually no current flowing through the switch, but anyway, the current flowing through this section, it's either here, you can put it here, or you can put it here, as if the switch is closed, so there's no current leaking through the lamp here. 1B1. The voltmeter reads 5 volt. Calculate the current in the resistance between A and B. So in this part. Okay, so there will be a current flowing here. And that current we can calculate, because the voltage difference here is 20 volt. So that means, see, all these nodes are connected, so the voltage difference here is also 20 volt, and we know the resistance of AC, so R AC is 40 ohm, so that means the current is then simply 20 volt divided by the resistance, 40 ohm, equals then 0.5 ampere. Okay, then 1b2. Calculate the resistance between B and C. Okay, what do we know about B and C? There is a voltage across of 5 volt. So the VBC is 5 volt. And we know the current flowing through it. The current is 0.5 amperes. So the resistance has to be the voltage difference across divided by the current, which we already calculated at 0.5. So it's 5 divided by 0.5 is 10 ohm. The voltmeter now reads 4 volt and the light turns on. Calculate the power at which the lamp lights. Yeah, so what happens when you close the switch? Then a current will flow here, and as a result the voltage here will drop. The resistance here, kind of the equivalent resistance from B through both this part of the resistor and the lamp, goes down. Okay, so let's want to keep so let's write this as circuit a little bit different, given that we have 2 parallel resistors here and 1 series resistor. So we can draw the circuit as this. We have a resistor here, then we have 2 parallel resistors, and one is the lamp, say R lamp, and okay, let's close the circuit here. And this resistor is the RBC, which we know is 10 ohm. This resistor is AB, and we also know what it is because the total resistance here is 40, so this is 30 ohm. So basically I'm just writing down everything we know and don't know. We also know the voltage across here is 20 volt. And okay, and then of course we know that the voltage difference here is 4 volt. That's what we read from the voltmeter. I think that's all we know. But it means that the voltage across here has to be 16 volt, using the Kirchhoff voltage law across the circuit. And we know the voltage across, we know the resistance, so we can actually calculate what this current here is. I is then 16 divided by 30 16 divided by 30 is 0.533 amperes. So we know the current going here. Okay, now what are they actually asking? After studying the circuit, the power at which the lamp lights. Well, the voltage across the lamp is a 4 volt given by the voltmeter, and then in order to find the power, we need to square this voltage and divide it by the resistance. But this is the unknown, so the question is, what is this resistance here? Okay, well, what do we know about these two parallel resistors? We know the total current going through it. So the equivalent resistance, of, how to write it down, of the two parallel resistors has to be equal to 4 volt divided by that current I just calculated. So that must be 4 divided by 0.533. That's 7.50 ohm. So I know the equivalent resistance of this R is 7.5 ohm. Okay, so with that I can then figure out what the resistance of the lamp is, and then I can figure out what the power consumed by the lamp is. Okay, so we use the 1R equivalent. So that's the calculation of the resistance of two parallel resistors that you have to know. 1 over then RBC plus 1 over RL. Okay, so it means that 1 over RL is just equal to 1 over R equivalent, which is given here, and then minus 1 over this BC resistor, so it's minus 1 over 10. And that means that RL is then basically the inverse of this. Oh, let me still write it. Oh, no space. So, of this here. So let's calculate that. 1 divided by 7.5 minus 1 divided by 10, which is 0.1 minus 0.1, then I need to take the inverse of that. So that is 30 ohm. And then finally the power consumed by the lamp is then the voltage of the lamp is 4 squared divided by 30. Which is 0.533, let's keep two significant figures, watt. Temperature of the black body and the wavelengths at which the emission is maximum. So I don't think I need this. And also remember Binas, if you forget the equations, Binas has a section about them. I think it's table 34, if I remember correct. Oh, 35, about radiation, wet van Wien. So it's lambda max is equal to times T. So okay, let me actually really. So lambda max is this constant kW divided by T. Okay, and this constant, then we need to go back to our constants section, kW 2.897, say 898 times 10 to the power minus 3 meter times Kelvin. Okay. And then the temperature was given, going back to the here, so the temperature is 3650 plus 273. Okay, I can do this by head even. So 923 Kelvin. Okay, that's good. Now we have everything. All right. I think there's something wrong. This is not visible wavelengths. I made a mistake. 2.898. That's better. I mean, always check what you get for if it's reasonable or not. We want something in the visible wavelengths range, which is hundreds of nanometer. Okay, so this is 7.39 times 10 to the power minus 7 meter. So that's 739 nanometer, which is kind of more useful of unit for wavelengths of light. Well, I probably should have kept one more. Yeah, I should keep one more digit, actually. Not sure if they're very strict about that. I assume so. So let's go back. 7 times 10 to the power minus 7. I think I can keep 4. So that is then 738.7 nanometer. Okay, 2E. The sliding contact at B is now also connected to Earth. Calculate the voltage between A and B. Alright, that's not too difficult. It means that VB is at 0 volt, ground, which I just define as 0 volt, and VA is, well, 20 volt less than ground, right? So it's negative 20 volt. So VAB has to be 20 volt too. And actually the lamp is off, of course, because both sides of the lamp are at ground in this case. Let's see what question 3 is all about. Oh, about gases. We have two containers, V1, V2, separated by a tab K, which is closed. The volume is given, the volume of the tubes are given. The temperature of volume 2 is given as well. Calculate the pressure in container V2. Okay, that's not too difficult. The ideal gas law, it's one of the things you definitely need to know, which says that the pressure times the volume divided by the temperature is N, the number of moles of the substance, times a constant R, the so-called gas constant, which I happen to know. So it is 8.314, but it is also in Venus. So in particular then means, let's call that P2 for the pressure in container 2 is then the number of moles. So, well, let me still, N R divided by the volume times the temperature. No, wow. Okay, have to pay attention. You need to multiply both sides by T. So divided by the volume. say volume 2, and the number of moles is 0.4. Then we have our gas constant, and then the temperature is given, and the volume is given too. So again, 0.4 times 8.314 times 298 divided by 30 times 10 to the power minus 3. Let's put it in the scientific notation. This is 3, and how many significant figures? We need to keep 2, because of the number of moles is known to that accuracy. So we get 3.3 times 10 to the power 4 Pascal. The tap is now opened. Both containers are kept at a temperature of 298 Kelvin. And volume 1 was in a vacuum, so container 1 was at vacuum. So effectively what it means is you have this container and you increase its volume from V2 to V1 plus V2. So now you can, let me see, oh, the temperature is kept constant, so what you in this case can use is that the pressure times the volume is constant. But the volume increases, so the pressure will have to decrease, obviously. So we then just said that so initially we have, so P initial times initial volume, which is just, volume 2. Is equal to the final pressure times volume 1 plus volume 2, which gives us an equation for P final as P initial times the volume 2 divided by volume 1 plus volume 2. And now we can just substitute the initial pressure, where I already erased it. What was the pressure again? I think it's only one significant digit. Then times 30 times 10 to the power minus 3 divided by 30 times, well, let's 30 plus 90 times 10 to the power minus 3. All right, calculator. Let's just drop these two. I get 30 divided by 120 times 3.3, and then times 10 to the power 4. Oh, okay, let's just, and then you get 8.25 times 10 to the power 3 Pascal. And I would round this to an 8.3 times 10 to the power 3 Pascal. Container V1 is then slowly cooled to 195 Kelvin, while container V2 retains its original temperature 298. Explain that the pressures will be equal in both containers. Yes, because any pressure difference will result in a flow between the two vessels, or how they call it, containers, that will equalize these pressures. I think that's probably sufficient there. Pressure difference, the molecules will move, and how much do you end up with in both? And that's exactly what they're asking. So calculate the number of moles of gas in container V1 after establishing the new equilibrium. Okay. Well, so what has to be equal between the two is the pressure. That's probably why question 3c is kind of a hint. So let's just write down what that means. Use the Cass law again to write down what that means. So the Cass law is P times V divided by T is nR. Remember that? So pressure for a given container at a given temperature, at a given volume with a certain number of moles of gas is then nRT divided by the volume. But on both sides they have to be equal. So let's call the number of molecules, the number of moles in V1 N1 and in V2 N2. Then we have, because so the pressures P1 and P2 have to be equal. We then get that N1 R is a constant, so N1R T1, which is different from T2, divided by volume 1, which is also different from volume 2, is equal to these at the second container. So this gives you a ratio of the number of moles. So we get N1 divided by N2 is then these things divided by each other. So multiply both sides by V1. We can divide out R and also divide both sides by T1. So you get V1 divided by V2 times T2 divided by T1. Yeah, that's it. Okay. And let's calculate that. So it's 90 times 10, I have that right, 10 to the power minus 3 divided by 30 times 10 to the power minus 3. And what were the temperatures? So V1, T1 is 195. And then T2 is still 298. Find that. So this is effectively 3 times this. That equals 4.58. Let's just keep another for good measure. Okay, so now we know the ratios of N1 and N2, and of course we know that N1 plus N2 has to be equal to 0.4. So we can substitute this basically 2 equations with 2 unknowns. And okay, so N1 divided by N2 is 4.585. That means that N2 is N1 divided by that number. So N1 plus N1 divided by 4.585 equals 0.4. So N1 equals 0.4 divided by 1 plus 1 over 4.585 divided by 1 plus 4.585 inverse is, let's just in the end keep 2 decimals, so that's 3.3 times 10 to the power minus 1 mole. For about nuclear medicine. All right. When ingested by humans, the element iodine is mainly absorbed in the thyroid gland. This property makes radioactive iodine isotopes useful for both examination of the thyroid gland and for treatment of tumors. So they talk about examination and about treatment. In both situations, a quantity of radioactive iodine is injected into the body, after which it decays in the thyroid gland by emitting radiation. Both iodine 131 and iodine 123 are used for examination and treatment of the thyroid gland. The thyroid gland can be examined by taking pictures of the thyroid gland with a camera sensitive to gamma radiation. Remember the 3 types of radiation: so gamma, beta, and alpha. Then iodine 123 is known to decay with a half-life of 13.2 hours by emitting only gamma rays. An iodine 123 nucleus is one of the reaction products in a nuclear reaction in which a tellurium 124 nucleus absorbs a proton. So this nucleus takes on a proton. All right. Give the reaction equation for the formation of this iodine from tellurium 124. So they say we have tellurium 124 and it takes on a proton, so we write it like this. So a proton has a 1 nucleon, of course, we call it P, and it has 1 proton, of course. And then we know it goes to, and we need to figure out how many protons there actually are in tellurium. It better be one less than iodine actually, otherwise this wouldn't be able to produce iodine. Let's so there's iodine 1, 2, 3. So with 123 nuclei. Let's go to Venus and look up these isotopes. There is a nice table for that. If I can find it. Isotopes. Starting with the atomic number, which is the number of protons. And tellurium, so 124 should be around 50, okay, 52. So tellurium has 52 protons, and iodine has 53, so that makes sense. So then, what else do we have? Obviously you can see this doesn't add up. We have 124 plus 1, it's 125. We should have 125 nucleons here. So what can you have with two nucleons inside? But let's also count how many protons. Actually, this 52 plus 1 adds up to 53, so that actually should be 0. So it should be something with 2 nucleons and no protons, and that basically means the only option is that it produces 2 neutrons. So neutron we can write as 1, 0, this way. So that should be this question. Yeah. For A. Explain on the basis of 2 arguments why iodine isotope is most suitable for thyroid examination. Well, which iodine isotope? Well, so iodine 23 decays by emitting gamma rays. So with a half-life of 13.2 hours, emits gamma rays. And then what about, I guess they mean iodine 131. That's the other iodine isotope. So let's go to Venus and look at, okay, there we have iodine 131 decays into beta, so these are electrons, right? Electrons plus gamma. So these yeah, and the half-life is 8 days. So yeah. They specifically ask here about examination, not about treatment. So in an examination, of course, you want to cause as little damage as possible. And in treatment, you probably want to cause some controlled damage to bad tissues. But for this, so you need to know the main difference between alpha, gamma, and beta, and in terms of ionizing power, actually beta minus is worse if the amount of these is the same, so the same activity. So the first reason to use iodine 123 would be that the damage per reaction is less. So this emits only gamma, while 131 also beta minus, which causes more damage. So in terms of ionizing power, beta minus is worse from gamma, and alpha is even worse from beta minus. Might that question come up? So that's reason one to pick 123. Then the other one is the half-life. The half-life of 123 iodine is 13.2 hours, which is much closer to a typical time during examination. You won't have an examination of, say, a week. So a lot of activity will go on for a very long time after the examination, which is not good. So half-life is closer to the typical examination time. Iodine 131 is injected in the patient, so I guess for treatment these are actually good. Then only beta radiation provides the internal radiation. The amount of I-131 administered to the patient is expressed in the activity of the iodine. And remember, that's one section in the syllabus is about that, so this is all stuff you need to know. The activity and number of decaying species, decaying nuclei, is actually proportional. So the higher the activity, the larger amount of radioactive nuclei you have. And that's log 2 divided by half-life divided by n, times n. And that is actually given in the syllabus, this equation. And it comes from, this is basically the derivative of the decay curve. So if you have a decay, this is the number of species over time, then the activity is actually the slope of this function. So that's why they express this in activity. Then they say to destroy a certain tumor weighing 2.6 gram, an amount of iodine 131 with activity of 7.3 gigabecquerel is administered. That's just decay per second, this unit. Now assume that only 0.12% of all administered iodine atoms transfer the energy released in their decay to the tumor. Calculate the dose that the tumor then receives. Alright, so what is dose? Dose is the energy per unit mass that a tissue receives. So it's energy per unit mass And they ask for that, so we want to calculate the energy. We know the mass. Well, how do we find the energy? We need to know what n is. N is the half-life divided by logarithm of 2 times A times the activity, which is given here. Oh wait, and we need to calculate the dose, so we just need to calculate the total number of radioactive nuclei that are injected, because that will form the total dose. I mean, activity only tells you how many per second, but the dose is actually when you accumulate all this. So, of course, over 8 days it will go down and it reaches 0. But what you really want to know is this amount here. Okay. And then we need to multiply it by the energy that comes free, and also times that percentage that is actually being absorbed. Okay, so what is the half-life then? Or let me first write an equation for the dose. So the dose will be this n times the energy that comes free in a decay. So let's look at our binos. Point six, and I assume it's MeV, 0.6 MeV. So times 0.6 MeV, and then times 0.12%. All right. And we want to convert this into joule, which is 8.0 days. So 8.0 days times 24 hours in a day and 3,600 seconds in an hour. So this is the number of seconds divided by log 2, then times 0.6, then times 10 to the power 6, and 1 EV is 1.6 times 10 to the power 19 joule. Remember that? If I can remember it, you guys can definitely remember. And then times 0.12%. Oh, I forgot to insert the activity. We need to times this, and because n is the half-life times activity here. Okay, so let me insert that here. (7.3 times 10 to the power 9 becquerel). So it's actually better if to to insert it here. It's more clear to the person looking at your answers. Let's do now the calculation. 8 times 24 times 3600 times 0.6 times 10 to the power 6 times 1.6 times 10 to the power minus 19 times 0.2, and now let me divide it by 100 because we talk about percent, and then multiply times the activity, which is this, and then finally divide by my log of 2. And I get 0.839 joule as the dose, as the, okay, I shouldn't have called this dose, I should have called this energy. This is the energy. And now the dose is the energy divided by the mass. So it's 0.839 divided by the mass, which was, where are we? 2.6 gram. 2.6 times 10 to the power minus 3 kilogram. That is 323 of joule per kilogram. 31 is excreted in urine. Urine contaminated with this may only be flushed down if the activity per milliliter does not exceed 1.85 becquerel. At a certain point, the urine collected from a patient appears to have activity of 1.5 megabecquerel due to the decay, and the volume of this is 1.2 liters. So that's probably exceeding quite a bit this requirement per milliliter. Let's actually calculate what it is. So for the, what is the activity at time 0 per milliliter? So times 0, let's call that A0, the activity is, well, 1.5 megabecquerel divided by 1.2 liter. So that's 1.2 times 10 to the power 3 milliliter. So that's 1.5 divided by 1.2 is 1250 becquerel per milliliter. So it is exceeding, it's exceeding what our requirement is. Alright, so now we wonder what is the activity as function of time. So activity as function of time is the activity at time 0 times the common equation for decay, namely 1/2 to the power time divided by the half-life. As soon as this reaches the limit here of 1.85 becquerel, then it's safe to actually flush it down. 1.85 becquerel per milliliter. And we have our A0 here. So what does that mean? At what time does that happen? So we need to solve this equation then. 1/2 to the power t divided by th is 1.85 divided by A0. That is 0.00148. Oh, that is right there, 1.48 times 10 to the power minus 3. Basically, you need to figure out 1/2 to power what is equal to this small number. So we just take the logarithm on both sides, and you get t divided by th times log 1/2. And you use the property that the log of some base to some power, this is a times the log of the base, and this is then the logarithm of 1.48 times 10 to the power minus 3. That means t divided by th equals log 1.48 times 10 to the power minus 3 divided by log 1/2. Is then 9.4. That's t divided by th. So that means that time is th times 9.4. And th is 8 days from the previous question. So we need to multiply this by 8. So that's, say, 75.5 days. So roughly 75 days you have to wait until the activity is small enough. Okay, moving on to question 5. Diffraction of electrons. Electrons behave like waves. If electrons are shot at a piece of graphite, a interference pattern can be created. This allows the distances between the atoms in graphite to be determined with a electron diffraction tube. And see this figure here. So we have a hot cathode that supplies electrons, that's here. It's heated, and these electrons that come free from it will have very small speeds. Then these electrons pass through an accelerating voltage that is variable up to 10 kV. The electrons pass through the piece of graphite, after which they produce an interference pattern on a fluorescent screen, which is here. The interference pattern can be explained by assuming that electrons behave like waves. Okay, so here with the hot cathode, here we have a potential difference of 10 kilovolts. Then the electrons hit the piece of graphite, and here we see a diffraction rings on the fluorescent screen. Then the following formula applies to the Bragg wavelengths. So this is the way I learned how to pronounce this name of a Belgian physicist, actually. And in this equation we have U here, which is the acceleration voltage. And we need to derive this formula. Okay, well, what you should learn, and it's part of the syllabus, is the so-called de Broglie wavelength. Lambda is h divided by p. So now we just need to see how we can, from there to here. Well, what's the, and p, so p is the momentum of the electron, so m times v, and that is, and somehow we need to see the connection between the momentum that these electrons gain and the acceleration voltage. Well, what we know is voltage is energy per unit charge, remember that. So the energy gained by the electrons during acceleration is the charge times the voltage difference, U. So it's E times U. And that will be converted into the kinetic energy of the electrons. So that's 1/2 m v squared. Well, why don't we just eliminate v and put the momentum in? So v is the momentum divided by m. So you get EU is 1/2 times m p squared divided by m. Now we want to isolate p, so we can substitute it here. And p is, oh wait, p divided by m squared, otherwise it wouldn't work. This m drops here, so you get 1/2m, so you get p squared is 2m EU. So p is finally the square root of 2m EU. And then we have proved that lambda is equal to h divided by the square root of 2m. Okay, they put the e in front, why not? E m u fkv. Okay, that's an easy question in principle. We just need to substitute whatever we know. Use your Bina's book. For the different constants that are needed. So here h 6.626. Is there anything about how many digits we need? Well, U, for example, is in 2 significant digits. Oh, it doesn't actually make sense to keep more than 3. So I just keep 3 here. Because that's how accurate we know the acceleration voltage here. 10 to the power minus 34 joule times second, but I won't list all the units. And then the square root, so 2, then the electron charge, 1.6, of course, 1.6 times 10 to the power 19. This one I actually remember. 9.101 times 10 to the power, also minus 31 kilogram, and then the acceleration voltage is 10 times 10 to the power 3 volts. Oh no, 5.0. 5.0, still 2 significant digits. 5.0 times 10 to the power 3 volts. Okay, so that's a little bit of a long calculation, but just plug it in. Open parenthesis 2 times 1.6. And I want to take the square root of that. Then I get 1 point, and I just keep 1, 2 significant numbers total, times 10 to the power minus 11 meter. The carbon atoms are layered on top of each other. In the individual layers, the carbon atoms are arranged in regular hexagons. The phenomenon of electron diffraction occurs within one layer and not between layers. Figure 2 shows one such layer. In a layer, the atoms lie in parallel lines, as indicated here. Reflection occurs on these lines. The electron wave that reflects from the different parallel lines have a different impasse length, which can cause them to interfere. This is shown schematically in figure 3. In this figure, ray 1 reflects from atom D, and ray 2 reflects from atom B. Okay. Then constructive interference occurs when this condition is met. 2D sine alpha is n lambda. This is an equation you should be familiar with. I think it's called Bragg reflection. But if not, then they give it here. So D is then the distance between these lines. Alpha is the angle at which the electron strikes the grid line, so indicated here, defined here. And lambda is the de Broglie wavelength of the electrons. Indicate on the answer sheet the difference in path length between ray 1 and ray 2 by drawing the path length difference more boldly. Okay. That is actually pretty easy. And that's why you only get 1 point for that. So this is 5C. Just copy it in. So we just compare the different paths for ray 1 and ray 2, and then you see that the additional path that is traversed by ray 2 is here. So make it bold. And here. I think that basically answers the question. And then there, with some math, I'm sure you can figure out that what actually this path length is. But they're not asking for that. What actually is the next? figure 4 here shows the various line on which reflection can happen. The distances between different lines are indicated by D1 and D2. There are actually multiple lines that are like regular. So lines here, this line, and also this line and this line. And they have to kind of repeat themselves. And with an interference pattern on a monocrystalline layer of graphite. So that's monocrystalline means only one crystal. The pattern of figure 5 is created on the fluorescent screen of the electron diffraction tube. So this is what you actually see on the tube. So on this screen here. And if the electron diffraction tube does not contain monocrystalline layer of graphite, but a polycrystalline layer, many crystals are crisscrossed. The interference pattern will look like in figure 6. So you see rings. And you have to see that like this. Just imagine if you rotate these different light points here. If you do that, then you will look at rings like this. And polycrystalline, you have many small crystalline layers that are randomly arranged. So each one actually will come at a different point, and if you have enough of them, then in the end they will form a circle. So explain whether the outer ring comes from reflection of lines with distance d1 or with distance d2. So we have to see it like this. We have our electron beam coming in. This diffraction gives kind of a diffracted beam at a certain angle. Let's call that angle theta. And basically, due to the polycrystalline nature, this thing is kind of rotated on the screen, so you get a ring. So you get a circular pattern, angle theta here. So you have to realize that in that equation above they were talking about a angle alpha. And let me again write that. So we had this situation. This is one of these crystal lines. This is alpha. So this angle is alpha. So what then is the angle theta? Well, this angle theta is the angle with the incoming electron beam. So if I extend this, then basically this, you can see that angle theta here is just twice the angle alpha. Which is the angle here in the diffraction equation for constructive interference. So now we have made kind of the connection to the location. You see this outer ring has a larger theta, and the other, let's say the inner ring here, has a smaller theta. So in other words, theta outer has a larger angle than theta inner. And now what does that mean for the distance, say, of the outer, or the distance between these crystal lines for the inner? Well, of course this also means alpha of the outer is larger than alpha of the inner, and that in turn means that the sine, since for angles in this question the sine is, if you draw a sine function, this angle can only be between 0 and 90 degrees. Actually, this angle is always very small. So in this region, the sine function is uniformly increasing. So it means also the sine of alpha outer is larger than the sine of alpha inner. The sine of alpha is inversely proportional to d. So to the sine alpha, and here we're really talking about the first maxima. So n equals to 1. The sine of alpha equals lambda divided by 2d. And from this, then, since they're inversely proportional, we then find that the outer must be smaller than the inner. So that means that outer ring is from D1. Low acceleration voltage, no rings appear on the screen. Then only the dot in the middle of the screen is visible. Explain why no rings appear on the screen at low acceleration voltages. Well, what happens at low acceleration voltages? Go back to our equation for the wavelengths, then lambda is proportional to 1 over the square root of the acceleration voltage. So if u goes to 0, then lambda will get large. You get very large wavelengths electrons. To d sine alpha is n times lambda. So the sine of alpha is n lambda divided by 2d. So so n is 1, 2, 3 for the different maxima. But let's take the first, n is 1. For that we have sine alpha is lambda divided by 2d. So you can already see if lambda gets larger and larger, this alpha will increase, but it can only go so much before the sign cannot increase anymore. So in other words, if lambda divided by 2d gets larger than 1, so no diffraction is happening. So no diffraction. Okay, a graph is made from the measurements in which the radius r of both rings is plotted against the Brownian wavelengths lambda of the electrons, see figure 7. For small deflection angles, the following approximately applies. R is 2 capital R divided by d lambda, and r is the radius of the ring on the screen, r is the radius of the sphere, of the diffraction tube, and lambda the de Broglie wavelengths, and d is the distance between lattice layers. Use the figure on the answer sheet, determine as accurately as possible the size of d for the outer ring. Okay, as an extra, which you don't need to do, just see why this equation occurs. So we have, say, our beam of electrons coming in, and where is it exactly placed? The piece of graphite is basically placed right here, and then we will have deflection due to the diffraction, and you get your rings here. So then we already saw that this theta here is the angle 2 alpha. But now they also say that the capital R is the radius of the sphere. So basically this distance here is 2 times R. That's twice the radius of the sphere. And R is the radius of the radius that you observe here. So what you can see is that the sine of theta is R divided by 2R. Now, for small angles, this is roughly equal to theta. So that's a common approximation we take. The sine of alpha, which is related to this angle theta, is lambda divided by 2d. And that also means for small angles that alpha is approximately equal to lambda divided by 2d. This is equal to, theta is roughly equal to r divided by 2r. So this is r divided by 4r. We get, well, multiply both sides by 4r. We get 4r times lambda divided by 2d equals 2r divided by d times lambda. And that is the equation that is there. And let's answer the question. Let's copy this graph. Determine as accurately as possible the size of the outer rings. So the outer rings are with the larger radius, so we need to look at the data on top. And let's get our ruler here and roughly put a line through. And yeah, like this. Now, I said before you need to draw this line as long as possible. However, in this case we need to be careful because the scale from 0 to 1.2 is kind of interrupted here. So we should not exceed this here. We just go to the area where it is like properly scaled from 1.2 to 2.0. So why don't we just draw it to 1.2 here? Okay, and then we can see here here. See, we're exactly at 1.2 here. So the slope, and of course why I want to look at the slope, because the slope equals 2r divided by d. And the r is given here by 65 millimeters. So knowing the slope, we know d. And then this is the delta, say, y divided by delta x. So delta y is 21.0 minus, I would say, 12.5. Times 10 to the power minus 3, then divided by 1.9, so this is 1.95, 1.98, 1.98 minus 1.2 times 10 to the power minus 11. So this is 8.5 times 10 to the power minus 3, and this is 1, no, not 1, 0.78 times 10 to the power minus 11. So that equals, just plug it in, 8.5 times 10 to the power minus 3 divided by 0.78 times 10 to the power minus 11. In this scientific notation, I get 1.09 times 10 to the power 9. So from here we can figure out what d is. Or d equals the slope, no, multiply both sides by d and divide both sides by the slope, then you get d is 2r divided by that slope. It's 2 times 65 times 10 to the power minus 3 meter, and divided by 1.09 times 10 to the power 9. So we get 2 times 65 times 10 to the power negative 3 divided by 1.09 exponent 9. So I get 1.19 times 10 to the power minus 10 meter. Let's see what they have here. 1.24. Let me see. Yeah, I think that's close enough within the accuracy of finding this line. So I think this will be counted okay. I would just keep one significant figure here. And in particular, time-wise, there's just a lot of work to do, and it's easy to make mistakes and get stuck at some of the questions. And some are not simple, like the power through this lamp, this diffraction pattern. So, well, I hope you guys will do well in the coming exam. And if you have any question or comments, just let me know.